All right, let's talk about Newton, Isaac Newton, who I introduced in the last video. I'm gonna talk about his first law. So he's got three famous laws. I'm sure you've heard about them, and they're actually very easy to understand. So I just want to go through the first law of motion here, and it says Newton's first law says an object at rest will remain at rest. And by the way, I want you to think about this. You know, when Newton discovered this, very little was understood about our world. So what I'm about to read to you, while it seems to be obvious at this point in our history as humans, it wasn't obvious back then. It was not obvious at all. And so this is a statement, and I don't want you just to read this and think, oh, this is obvious. This is something that is still considered one of the greatest achievements of humankind. These three laws. And the first one says an object at rest remains at rest, and an object in motion continues in motion with a constant velocity or constant speed in a straight line unless the object experiences a net external force. So there's a couple interesting things here. So this part here, an object at rest remains in rest. All matter, anything with mass, has a property that's known as inertia. And so Newton's first law is sometimes known as the law of inertia. The more mass something has, as the mass of an object goes up, as mass goes up, inertia goes up. Bigger objects have more inertia. That's why an elephant has trouble running and cutting and changing direction, whereas a little mouse can easily go back and forth zigzagging because it's got very little mass, so it's easier for it to change direction. Anyways, an object at rest remains at rest. So the more inertia something has, the more its tendency is to stay at rest. Or if the object's already moving, it will continue to move unless there's some outside force acting on it, okay? This is Newton's first law. Basically in a crux. So what we're going to do now is I want to put on the video of a movie here, and I want to watch this and talk about what's happening. All right, so in this clip we're going to see George Clooney and Sandra Bullock, and we'll talk about what's going on here and how it relates to our Newton's first law.
Explorer, this is Houston.
Go ahead, Houston.
Mission abort. Repeat. Mission abort.
Explorer, this is Kowalski confirming visual contact with debris. Debris is from a BSC stat. Repeat. I have a record.
Dr. Stone requesting faster transport.
We have to go. We have to go. Go,
Kennedy
go.
reports meteorological conditions. Don't go.
Houston, Explorer, copy. Explorer, Dr. Stone requesting faster transport to Bay Area. Explorer, do you copy?
Explorer, permission to retrieve Dr. Stone.
Your go, Kowalski. Houston, this is Explorer, copy.
As you watch this clip, I want you to focus. The only way these astronauts can move, and this is realistic here, are with these jetpacks. So the jetpacks provide a force, and that force overcomes their inertia and allows them to start moving. And so as you watch this clip, there's going to be a scene where one of the astronauts just lets go and his jetpack doesn't work anymore, and he just keeps floating and floating into outer space. And we see that an object in motion continues in motion unless it experiences an external or an outside force. But in space, there is no outside force, and so that would be death. If you jetpack ran out, you would just float away forever until something were to exert a force on you. And so this is a great illustration of Newton's first law here. Let's continue to watch it.
All right.
We've lost Houston. We've lost Houston.
Look, we need to get the hell out of here. Need some help there, man? No, don't wait for us.
It's stuck.
Man down.
Houston, this
Man
is
down.
copy. Houston, Explorer, copy. Kowalski,
Explorer's been hit. Explorer's been hit. Explorer, Explorer. Astronaut is off structure. Dr. Stone is off structure. Dr. Stone, detach. You must detach. If you don't detach, that arm's going to carry you too far. Listen to my voice. You need to focus. I'm losing visual of you. In 2 seconds, I won't be able to drag you. You need to detach. I can't see you anymore. Do it now.
Let's fight.
Houston, I've lost visual, Dr. Stone.
So not sure how many of you have seen that movie, but in seeing that movie, when I saw it, I immediately thought of Newton's first law. That last scene, she just goes off and into space, and there's no force to stop her, so her inertia continues to carry her. And so that's a good illustration of Newton's first law there. All right, so let's talk about a physics concept. A physics concept called the net force. Okay, so when we look at Newton's first law, it says there has to be a net external force. But what does that mean when we say net force? So the net force is the sum of all the forces acting on an object. So let's take, for example, here we've got this car full of different colored objects, and we've got these robots, and they're pulling on it with a rightward force. So Newton's first law, that an object will remain at rest unless the object experiences a net external force. So here's an example where there's a net force. There's only one force, and it's in the rightward direction. So as we watch this movie, we should see this car move to the right. So we see the robots, they're about ready to start pulling. And you can see that they have a net force, and so Newton's first law says the object will remain at rest unless there's a net force. So there is a net force, so it will move. Now let's put equal forces on this. So I'm going to put two robots of equal, or two of the same types of robots in each side. So now we see that there is no net force. Here we would say the net force equals 0 newtons, because the forces are exactly equal and opposite. Okay, but then I add a third robot here, and the net force in the leftward direction is slightly bigger, so the object will move to the left. Okay, so that's the idea of net force and how it applies to our situation with Newton's laws, Newton's first law. All right, so let's look at this situation. Here's a practice problem, and again, if you want to use the ebook, this is on page 126 of the ebook. Okay, so we have a situation where Derek leaves his physics book on top of a table that is inclined at a 35-degree angle, and the free body diagram is pictured here to the right. So hopefully now that you can find the free body diagram, or can draw the free body diagram. All right, so this problem has a couple steps with it. The first thing is we need to figure out all the forces to find the net force. But you see this force here, you can consider to be at an angle. And so whenever you have a problem where there's a situation where the object's at an angle, you have to switch your coordinate system. In other words, normally we say this is x and this is y. And that works for most physics problems. But in this physics problem, the table's been, or the book's on a table at an angle. So what we have to do is we actually have to take our coordinate system and we have to rotate it to fit our situation. So we can see here, I now make this direction the x direction and this direction the y direction. Okay, so all I've done is moved my coordinate system to match my free body diagram. All right, so the first step, and you don't always have to take this step in a problem where you're finding the net force, but is to select a appropriate coordinate system. So we've already done that. We know our coordinate system now looks like this. So I'm going to move this over here, and let's shrink that down a little bit if we can. Okay, so there's our coordinate system. So that's step one. Okay, so the next step is we need to find the x and y. Find the x and y. All right, it's giving me trouble. So find the x and y components of all vectors, of all force vectors, right? Okay, so that's going to be our next step. So when I find the x and y, I can make a little chart where I do my knowns. So I do my knowns here. So we look at our free body diagram, and the first force we have is in the y direction. That's the force of the table in the book. And remember, our coordinate system is here, right? So this is now the y direction. So my first known, so I'm going to do forces in the y first. So my first force is force of table on book, and that is 18 newtons. Are there any other forces in the y direction? Well, this force isn't quite in the y direction. If we look, we take our coordinate system, we see that this force is actually at some angle, right? It's at an angle. So we've got to draw this triangle and figure out how to find the y component of this force. So what I'm going to do is I'm going to come down, I'm going to magnify this, I'm going to bring this, whoop, can't bring that down. I'm going to redraw the picture down here, and let's look at the triangle that we can form. This is what our triangle looks like, and I'm just looking at this force, so it's the 20 newtons. Now, since we know this is 35 degrees from the problem up here, we can see that right there. So what I'm going to do now is I'm going to draw my x and y components. So we'll do, here is the, let's do that in black. So here is the y component. So we can call this force the force of gravity in the y direction. And then we'll do in blue, I forgot to put the arrow on that. And then we'll do in blue, force of gravity in the x direction. Keep in mind, this is now the x direction, this is the y direction, right? And we know gravity is going to pull the box down the slope that way, and the y direction is this way. So, so here are our two components, the y direction and the x direction. Now, the right angle should be here. It's not going to be here between the red and the blue. It's going to be between the black and the blue for any problem like this. And it also turns out that since this angle is 35, these are similar triangles, and the inside angle here, this angle here, will also be 35. So what we have is we now have a triangle where this angle is 35, and we know the hypotenuse. So we can use sine, cosine, and tangent to get to our x and y components. All right, so using sine, cosine, tangent, if I have this angle, I know the sine is opposite over hypotenuse. So using this triangle, I use the sine of 35. So let's find the force. Let's find the force. Oh, that's not cooperating with me. Let's find the force of gravity in the x direction. So that's going to be the sine of 35. Right, since sine is opposite over adjacent, here's 35, so the opposite side is fg of x. So sine of 35 equals the force in the x direction over 22 newtons. So we get here, we get a force in the x direction of 13 newtons. Right, so there's our f of x. So I'll move that over here to our knowns. And then we can now find the fg of x, or sorry, fg in the y direction is now, if we look at our triangle, here's the angle, and it's going to be the cosine of this angle. It's going to give us the adjacent side, which is fg of x. So, and keep in mind, this is different than normally. Normally, you would use cosine to find x and sine to find y. But when you have something on an incline like this, so cosine equals f in the y direction over 22 newtons. And this gives us an fg in the y direction is equal to 18 newtons. All right, so we'll take this and we'll move this over here. So we now have fg. See if I can circle that there. Circle that like that. right? So I have FGY and FGX. So I'm going to get rid of my triangle here. Give me some room here. Let's see if I can get this. I'll just move it back up. Move it over here, right? So now I have forces in the X and the Y. So my total forces now, or my new picture will look like this. So here's the book on the incline. So now I've got a force downward of 18 newtons, and I've got a force upward of 18 newtons. That's this force, right, which is at 18. We just found that this 22 Newton force has a force in the y direction of 18, okay? I then see that I have a downward force of 13 newtons in the x direction, and that came from here, and I have a force of friction in this direction of 11 newtons, okay? So the original question said, what is the net force? So when we're finding the net force, we find it in both the x and y direction. So our third step, find force net, and the net force is often written. So let's see, find force net in both x and y. Okay, and the way we show the net force, it's the Greek letter sigma, and that means the sum. So we'd say the sum of the forces in the y direction. So right here we see the sum of the forces in the y direction, and we see that 18 in the positive y and 18 in the negative y, so we know the sum of the forces in the y direction is 0 newtons. And then we make the same sigma, so it's the sum of the forces in the x direction is equal to, now here we have 13 newtons down and 11 newtons up, so it's 2 newtons. And then we can call this, we haven't labeled this as our slope here as positive or negative. Usually this would be positive and this would be positive, so it's a positive 2 newtons. So our net force is a positive 2 in the positive x direction, or it's 2 newtons in the positive x direction, okay? So I know this is a long video, but this will take place of a practice problem video, but this is how you do a net force calculation when it's on a slope. I hope that was fun. I know it's a little long, so I'll let you go.